Hi, grade 12s. We're on our second day of sinusoidal functions. The word problems that I gave you yesterday were a challenge, so I hope you thought hard and learned a lot from the stress of that. But in particular, we have noticed that sinusoidal functions, although primarily to graph sine and cos, can model circular situations. So this Karen had a water wheel. We certainly do lots of problems with Ferris wheels, how far you are from the ground. Other typical problems that we use to model circular situations could be the orbit of the Earth about the Sun or the Moon about the Earth. Anything that's relatively circular can be a periodic sinusoidal function. So related to that could be sunrise times based on our orbit every year. Depends on how early or late the sun rises, winter, summer. Depth of the tide is also based on the movement in a circular way of the Earth and the Moon and all of that. Just to recall, we did a table of values to set out the primary sinusoidal functions y equals sine x and y equals cos x. So from the table of values, you should have a copy of the sine curve. For y equals sine x, we begin at 0, 0 because the sine of 0 is 0. Sine of 90 is 1. So we've got these particular points that we can anchor ourselves to when we draw. Sine of 180 degrees is 0. Sine of 270 is -1, and sine of 360 is 0 again. So we have a curve that follows those strategic points. So that is something you're going to want to have at your fingertips. I'm trying to draw quite smooth. It's not sharp like a set of teeth. It curves as we saw from our table of values. So that would be your sine. It would go left and right forever. We also wanted you to look at some important key features, the domain of the sine, as x can be any real number. For y equals sine x, we looked at the range, and we noticed that there are maximum and minimum values for y, and y lies between -1 and 1, and all the bits in between. So we could write the range as such. Other key features we asked you to look at was the y-intercept. For y equals sine x, we have a y-intercept at 0. But notice we have lots of x-intercepts. X-intercepts are multiples of 180 degrees. And we also looked at the period. The period is the time that it takes basically, or the degrees that it takes to run one full cycle. So with sine, I started basically in the middle of that wave. I go up, back to the middle, down below, back to the resting point. So the period takes 360 degrees to complete, and then it will do exactly the same cycle again. We are looking for the axis. And the axis is that point of rest, that line that runs right through the middle of our sinusoidal function. And for this one, it is along the x-axis. We haven't moved it up or down at all. It would be y equals 0. The amplitude is how high above that line of rest we go and how far below, and the amplitude is 1. 1 above the x-axis, 1 below the x-axis. And the maximum and minimum values which come from this. The maximum is +1 and the minimum is -1. I think that's all the things we looked at yesterday. Then we compared that to cos x, and there's more similarities than differences. Y equals cos x, however, the cos of 0 is 1. So we start at 1 for cos x. Cos of 90 is 0. Cos of 180 is -1. cos of 270 is 0, and cos of 360 is back to 1 again. So this one starts on its maximum value and returns to maximum value in 360 degrees. So for y equals cos x, the period is the same, 360 degrees to complete a cycle. The axis is the same. The amplitude is the same. It's 1 above that line of rest and it's 1 below. Our maximum is 1 and our minimum is 1. So far everything has been the same. The y-intercept, however, for y equals cos x is 1 instead of 0, 0. The x-intercepts also are different. They would be 90 degrees, 270, and so on. The domain and range are the same. Your domain can be any real number, and your range lies between -1 and 1. We're going to get a little messy with a couple of these. We're going to graph some things that are a little bit more interesting. So for the first one, y equals sine x minus 30. So we're going to create a table of values and figure out our graph. Put a few key values in. 0, 45, 90, 180, 270, 360 to get ourselves started. I'm going to pop 120 in there as well. If x is 0, we are finding for our y value, y equals sine of 0 minus 30 is negative 30. So let's type into our calculator sine of minus 30. It's negative a half. Sine of 45, so, sorry, y equals sine, and we're going to put a 45 minus 30 is 15. So what is sine of 15? 0.26. We put a 90 into our equation. It's 90 minus 30, sine of 60. We already know what sine of 60 is. It's root 3 over 2, or 0.866. Sorry, that's a 6. If I put 120 into my equation, I'm going to be doing 120 minus 30, which is 90. We already know what the sine of 90 is. 1 sine of 100, so sine of 180 minus 30 is 150. We know what sine of 150 is. It is a half. 270 minus 30 is 240. Sine of 240. Negative 0.866. And if I put 360, 360 take away 30 is 330. What is sine of 330? It is negative a half. So we've got some values to graph. So when x is 0, let's put on some values here. There we are. When x is 0, my new function is at minus 1/2. A new y-intercept. When x is 45 degrees, so I'm looking right in the middle here, I'm going with 0.26. So about right there. When it's 90, I have 0.866. So out right there. When I have 120 degrees, it's 1. So there looks to be a maximum. I've skipped a few values in here just to get us anchored. When x is 180 degrees and I put it into that function, I have 0.5. At 270, I've got minus 0.866. At 360, I've got minus a half. So to follow the scant points that we have, it appears that my maximum is at 120 degrees. For our normal y equals sine x, our maximum used to be when x was 90 degrees. So it looks like I have moved this graph to the right from where it would normally lie, 30 degrees. Interesting. Y equals cos x minus 1. Let's come up with a table of values. So 0, 45, 90, 120, 180. These seem more arbitrary than they're supposed to be. 360. I'm just grabbing some values so that I can get myself anchored. If y equals cos x minus 1, I know that the cos of 0 is 1. 1 take away 1 is 0. So I'm going to have a starting point here. When x is 45, cos of 45 is 1 over root 2. 1 over root 2 take away 1. I'm typing that into my calculator. Minus 0.3 approximately. Cos of 90 is 0, and 0 take away 1 is negative 1. 120. Cos of 120 is minus a half. Minus a half take away 1 is minus 1.5. That's one we haven't seen before. Cos of 180 degrees, we're back to negative 1. Negative 1 take away 1 is negative 2. Cos of 270 degrees is 0. 0 take away 1 is negative 1. And last one that I'm choosing, if I don't have enough values, I will do some more. Cos of 360 is 1, and 1 take away 1 is 0. So let's plot these and see what we've got. We've got 0, 0. We've got 45 matches with negative 0.3. So if we do negative 1, 1, about here. All right. 90 goes with negative 1. 180 is with negative 2. 270 negative 1, and 360 0. So it looks from my points that I have a cos curve that is doing this. And I say cos because on our original y equals cos x, it was from a high back up to a high again in 360 degrees starting when x is 0. This is following the same pattern. It's really lumpy, but it's following the same pattern, just that everything has been shifted down 1. Interesting. Lastly, for this, well, not lastly, but in the middle here, we're doing two different things. In brackets, we're adding 60, and outside of the brackets, we're adding 2. So let's determine a few points here. Okay, get us anchored. I'm going to substitute a 0 in there. So I am putting a 0 into the bracket. First of all, sine of 0 plus 60 is sine of 60, which is root 3 over 2, 0.866 plus 2, 2.866. It's easier to plot when we have decimals. Sine of, I'm putting a 45 into the brackets. 45 plus 60 is 105. Sine of 105, I haven't got a clue. So I'm going to type it into my calculator. I get 0.9659, add 2. 2.9, sorry. 6. Sine of 90 plus 60. 90 plus 60 is 150. Sine of 150 is a half. A half plus 2 is 2.5. Sine of 120 plus 60 is sine of 180. Sine of 180 is 0. 0 plus 2 is 2. 180 plus 60 is 240. Sine of 240 is negative root 3 over 2, which is negative 0.866 plus 2 is 1.13. Just a couple more. I'm going to put 270 into the brackets. 270 plus 60 is 330. Sine of 330, now we've done this, but I don't remember. Minus a half. Minus a half plus 2 is 1.5. And 360. 360 plus 60 is 420. Sine of 420 is root 3 over 2, 0.866 plus 2. All right, at the very least I see a pattern. Let's plot our points. So when x is 0, Let's go with 1, 2, 3, -1, -2, -3. So it's condensed. It's going to look a little bit different. 2.866, about right there. For 45 degrees, we're looking at 2.966, which is a little bit higher. And for 90, it is 2.5. 120 is 2. 180 is 1.13. 270 is 1.5. 360, 2.866 again. There we are. It's hard to know for sure if I've got enough points to graph that, but it gives us an idea. It appears that our sine curve has moved to the left, and it normally starts at a mid. Let's see, about here. Or here would be our normal start. And it has also been moved up. So we've had two things go on. It's been moved to the left or to the right, and it's been moved up by the translations that we've done. So to summarize, if you put something in the brackets, that will move it horizontally. It will take your sine wave and will move it to the left or to the right. If I have x subtract a number as I've got it in this form, I am moving it to the right a degrees. If we add b on the end, so we're adding a number on the end of our sine or cos function, this is a vertical translation. If I am adding a number as I've got it written here, it will be up b units. So let's graph this without a table of values. So for the first one, I've got x subtract 15. Subtract 15 actually means to the right 15. And that's the one that's hard to remember. Anything in brackets can be backwards. Subtract 1 on the end means down 1. It's a vertical change. It's subtracting, so it's going down. So in the back of my brain, I have to have my regular sine wave. Remember that it starts at 0, 0. It goes up, up to 90, back to 180, 270, 360. So in dots is my regular sine wave. The one that I'm doing is to the right 15 degrees and down 1. So my starting point is no longer at 0, 0. My starting point is 15 over. So I have to, on my scale, that's half a square and down 1. So my starting point is now going to be here. Half a square to the right, 2 squares down. I'm going to take all my major points and do that. I'm going to go half a square to the right, 2 squares down. This one, half a square to the right, 2 squares down. And my curve is going to follow that pattern. I have an extra blue blip I didn't mean to put there. Okay. Up, back, minimum, up. And it would continue that way. So I've moved it to the right 15 degrees and down 1 full unit. The next one, y equals cos x plus 45 plus 2. I always take a moment to write it in English. So in the brackets, I have a horizontal change. My left rights are always kind of backwards. It's plus 45, it's actually left 45. And then the plus 2 is vertical change. and it is as you would think it would be, it's up 2. So I want to take my regular coast curve, which I'm going to do as a dotted, and I am going to move it up 2 and left 45. So if I'm going to move something up 2, I better make these increments a little smaller. -1, -2, -3, and so on. My normal coast curve starts at 1, and it goes through 90, low at 180, through 270, and so on. You will need them in front of you while you get used to doing this. We're going to go to the left 45 and up 2. I'm going to do both things at once, and I'm going to do it with the major point. So I'm looking at this point, this point, this point, this point, and this point, and then I'll just fill in the curve from there. So left 45 is like 1.5 squares up 2. So kind of left 45 up 2 would be here. Looking at that guy. And the next one, left a square and a half up 2. This guy. Left a square and a half up 2. This one. Left a square and a half up 2. Does that look right? Yep. This one. Left a square and a half up 2. There. The blue dots form my new curve, which should be left 45 up 2. And this is not a very smooth curve. I did the best I could. There. Two things going on here. We have a horizontal change, and in brackets, remember, be careful, it's going to be to the right 90. On the end, we have our vertical change. It is up 1.5. So we are going to put in dotted line. It helps my eyes. I hope it helps yours. I am going to put my original sine curve. My original sine curve starts at 0, 0, goes up to 90, passes through 180 as it goes down at 270, and up to 360. That's my original y equals sine x. This one has a horizontal translation, right 90, which is 3 squares, and up 1.5, which is up 3 squares as well. So I'm going to look at my major points. This one, this one, this one, this one, and this one. So the first one, right 90, which is 3 squares, and then up 1.5. That is my new starting point. The second dot, the second little circle, I am going 3 squares to the right, up 3 squares. So I'm off the page here, but that's all right. The second little circle, over 3 squares, up 3 squares. Fourth circle, over 3, up 3, over 3, up 3, again off, but that's all right. My curve looks like that. And it would continue with the same pattern as we go to the left. There. There's some questions for you to try. You can't do these without experimenting. Page 28.